in the rest of this lecture, we are going to look at linear approximation and error estimation. Now, essentially, this is just applications of tangent planes. That's all it is. You've got some crazy surface. The function associated with it is difficult to deal with. Well, let's simplify and use a tangent plane, because the tangent plane is easier to work with. Okay. Now, let's start with the definition. The linearization of a function f at a point, assuming f is differentiable, is the following function. Now, I'm actually going to change the notation here to an a. I don't like that L because you might confuse it with the linear operator from a few lectures ago when we talked about differentiability. So I'm actually going to go through and just change these big L's. Now, can anyone, well, I guess you can see it here. This function of two variables here is just the tangent plane to the surface of the function of interest. Now, if f is smooth enough, and I haven't said what I mean by smooth, I will in a minute. If f is smooth enough, then the tangent plane is actually a reasonable approximation to the function. So first of all, let me show you what I mean by smooth. We have an idea of what we mean by a smooth curve. Right, can anyone remember the definition of a smooth curve? Sorry, say again? Yeah, right. So I guess technically speaking, that's geometrically absolutely right. It's smooth. I guess when we talk about a smooth curve, we mean that the tangent vector is non-zero and is continuous. Okay. So in other words, smooth curve always has a non-zero tangent vector that's continuous. What do we mean with surfaces, though? That's a little bit more difficult. I'm not going to give you a full answer for that because that would take too long. You'll see that in the second half of this semester. But by smooth, a good way of thinking about smooth surfaces is that the surface will be smooth if it has no corners or folds or sharp peaks. So on the left, we'd say this surface is smooth. And over here, you can see we've got all these folds and stuff. Not smooth. Now, I mentioned that for these sort of smooth surfaces, the tangent plane will provide a reasonable approximation to the surface near the point of interest. So let me just sort of roughly justify that. Here's a function of two variables. Now the graph there, okay, I've just done it using Maple, using the plot3d command, which is very useful. The graph is not the surface there is not the graph of that function. What I've done is I've actually used Maple to plot the graph of the error between the function and its tangent plane. Okay, so what does that mean? Well, let's have a look. I know it's a bit hard to see on the screen. If I'm at 0, 0, and I sort of don't walk away from 0, 0 too much, that surface doesn't rise very much and it doesn't fall very much below the xy plane. But as soon as I start moving a fair way away from 0, 0, say over here, let's say, I don't know, some point over here, I can see that the curve is going down below the xy plane. So the error would be large and negative then. Okay, so at least from this picture, it looks like if I've got a smooth surface and I set up a tangent plane to a certain point, then the tangent plane will be a reasonable approximation, as long as we don't move away from our point of interest too far. Okay, the first, I'm going to change this to an A. Now the first question is, well, how good of an approximation is it? This slide's about the standard linear approximation. So if f has continuous partials up to the second order, and we have some sort of rectangle centred at our point of interest, and m is a bound on these, so in other words, these are less than or equal to m, then the error, defined by this function e, between the function f and its linear approximation, which I've changed to big A, is less than or equal to this. Now you might think, well, so what? Well, what does it mean? Well, it means that our polynomial A gives a so-called first order approximation to f near this point, okay? In the sense that the two curves touch at our point of interest and this limit holds. In other words, the error is negligible when you compare it with this. Now, a good independent learning exercise is to show that if this holds, then this limit's 0. If you have time, you should try to do that, because it will test you on evaluating limits. Okay? I'll give you a hint. Young's inequality comes into it as well. Now, we're not going to concentrate too much on this, but it is nice to show this to show that if this holds, then this holds. I'm not going to prove it. The basic idea relies on Taylor polynomials of functions of two variables. We'll do that next time, okay? So I'm not going to prove it. But how can we use the tangent plane to form some sort of approximations? That's really what we want to talk about in the rest of the lecture. Now, if we use this kind of approximation based on the equation of a tangent plane, for these small quantities, delta x and delta y, you can see that we've got some sort of approximation, as long as these two things are small. Now, how is this important? Well, when we take measurements of anything, really, our measurements are never really exact. Okay, there's always a little bit of play involved. So this sort of raises the question, if I measure something and have small kind of changes in the measurements, does it affect the overall calculation or the overall results in a huge way? So that's what we're going to look at. We're going to estimate the error and I guess also sort of look at some error bounds. Okay, so some important notation. This delta f is called the increment. Now, it's just a value. Here, x naught, y naught is some point, and the point of interest, x naught, y naught, is usually chosen so it's easy to work with. Okay, so f at x naught plus delta x, y naught plus delta y, this may be something that's difficult to actually work out. But we can approximate it, I guess, with something a little simpler. Now, if we go back to 5 and just sort of rearrange, bring that over to the other side, there, and then under this notation, we have this type of approximation. So you can think of delta F as being some sort of error, really. If you take absolute values in 6, and then use a triangle inequality, so by the triangle inequality I mean something like this. Okay? Then you can come up with 7. So 6 and 7, from a practical point of view, are really what you want to remember, what you want to call on when you're asked to do these error estimation problems. Okay? You don't need to remember them both. All you really need to do is remember 6. Okay, if you know 6, you can get 7 just using the triangle inequality. Now, as a general guide for the practical use of these two, 6 is useful for approximating errors, while 7 is useful for estimating maximum errors. So 7 would be used when you want to see, well, what's sort of an upper limit on the worst case scenario, the largest sort of error. So let me show you an example, and let's see how it works. So here's one I've created earlier. Now, even if you don't know anything about circuits, you can still do this question just by applying the stuff on the previous slide. Okay? So in a basic sense, we've got a function of 2 variables, and we're told that x is decreased by 1.5%, y is also decreased, but by 0.5 of 1%. Find the approximate percentage change in f. So how do we do it? Well, if we're going to use the ideas from the previous slide, then we have to come up with some values for delta x and delta y. Now, if we just read back the information that we're given, we're told that the change in x delta x is minus 1.5% of x. Okay, so I can write it like this. And the same with delta y. Now, our approximative type formula involves partial derivatives. So we can now take our f, differentiate, and I'll get the following parts. So, putting all this stuff together, we end up with the following. And now, essentially, what I'm going to do is try to simplify as much as possible. Okay, so I've simplified there. And, I mean, you don't have to do this, but what I've recognized is that I can take out a common factor here and here. So that's where the f comes out. You don't have to do that. You can just divide both sides by f if you really want to, and you'll get cancellation. Whatever you feel more comfortable with. Okay, so then it's just a matter of simplifying and rearranging. Remember, we're after the approximate percentage change in f. So that's a basic example. I've gone through it quite quickly because it was pre-prepared. That would be sort of low to medium on the difficulty scale. Low to medium. But these type of questions I've seen them in class tests all the time. Okay, they're not difficult as long as you can remember the approximative type formula. Okay, let's do a slightly more practical one. Consider a cylinder with base and height. Okay, so here's my dodgy drawing. And we measure the radius and the height, and our instruments tell us that R0 is 5 centimeters, and the height, H0, is 12 centimeters. Now, our measurements are calculated to the nearest millimeter. So what does that mean? Well, we don't know what, in this case, delta R and delta H are, but we know we can estimate them in the following way. So let me show you. So delta R is less than 0.5 of a millimeter. Now I'm going to change that to centimeters because it's, we want to work in all the one type of units. And the same with delta H. Okay, so we are going to use this now. Okay, we've got the estimates for these with, I guess, with x and y replaced with h and r or something, and this is what we're chasing. We want to come up with some sort of expectation for the maximum percentage error in calculating the volume. Okay, So we also want to have some sort of function of two variables. And we're going to use 7, our expression 7. Okay. So to use 7, we need to take the partials. So V sub h is going to be pi r squared, and V sub r is going to be 2 pi rh. All right, so let's use our 7 and see what we can come up with. And now all we have to do is work out these little bits. So this, when h0 equals 12 and r0 equals 5, we're going to get pi times 5 squared. Now, delta h is less than or equal to 0.05. So I'm going to change that to a less than or equals to, because I want to put that in now. And this, we just evaluate this at our point of interest. So R0's 5, H0's 12. So now it's just a matter of simplifying that down to some number. Well, you can you can get rid of the absolute values because all of these things are positive. I've got a common factor of 0.05, 5, and pi. So I'm actually going to take those out. And what am I going to be left with? I'm going to be left with 5 in there, and 2 times 12 there, so 24. So if you can simplify this down to now, we're actually chasing some sort of estimate for the maximum percentage error. So we're not quite done yet. We want to get an estimate on this. So I've got 29 on 4, 29 pi on 4, divided by the volume on our measurements. So that's going to be pi times 5 squared times 12 times 100. Okay, so simplifying that, you should get about 2.42%. Sorry, it should be less than or equals to. Yep. Okay, so what does that mean? It means that under our measurements, kind of the worst case scenario is that you're off by 2.42% in your calculation of the volume. Now, the next question is, well, is that acceptable? If you go to your boss and say, well, I've done my measurements, and the worst case scenario is I'm out by about 2.5%. Is that reasonable? Is a 2.5% error reasonable? Well, it depends. It depends on the problem, I guess. Okay, so those problems aren't too involved. There's just a little bit of computation. Now, something that you may have seen in first year is this idea of a total differential. Now, if we introduce these differentials, dx and dy, they're actually independent variables, and we can assign them any values. In the context of this lecture, what we can do is let dx be whatever delta x is and dy be whatever delta y is, and then we can come up with this definition of this total derivative. Now, how does it relate back to what we've just seen? Well, for these values, we have the following. So df and the increment of f are the same, and we come up with this. Now, there's one last problem to do that we're going to do together about manufacturing cylinders. So let's have a look at that. So, a manufacturer produces cylindrical storage tanks with height 25 meters, radius 5 meters. And suppose you're looking after quality control in the company. What you're asked to do is to perform an analysis on how sensitive the tank's volumes are to small changes or variations in the height and the radius. And in particular, your job is to come up with one of these measurements to really closely study. Which one? Should it be the radius or the height? It's a good question. It's a good question. Anyone want to suggest how we might determine that? What do you think? So will a small change in the height lead to a massive change in the volume, or will a small change in the width, in the radius, lead to a massive change in the volume? What do you guys think? Radius. Why? Squared. But what if the radius was really small? If you're squaring, let's say the radius was a half, and you're squaring the radius, you get even a smaller number. So it kind of depends on the measurements, right? It kind of depends on the measurements. So let's actually perform the analysis and see what we come up with. Now you're right, by the way, it is the radius for this one. But for this one, it's the height. Okay? So, again, we have our function. So this is part A, I guess. I've kind of switched these things around. Hopefully it's not confusing. Okay, so let's work out these partials. So if I take the partial with respect to h and then put in r naught, I'm going to get something like this. Well, I'll put it in a second. Okay, so let's sub in r and h naught. I can take out a pi. So 2 times pi times 5 times 25. That's actually going to be 250. Now, what does that mean? Well, it means that if there's a 1 unit change in the radius, it's going to be a 10 times more than a 1 unit change in the height, because you've got this sort of, you know, this 250 is 10 times 25. All right, so if you change the radius by 1, you're actually going to contribute 10 times more to a change in the volume than a 1 unit change in the height. So for part A, this would be your conclusion, and your conclusion is pay attention to the radius measurements. So for part B, I've left it as an independent learning exercise. Well, actually, it's switched over.